Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
It's a great pleasure for me to introduce the first colloquium of the quarter, as well as the initial talk in hopefully a long series of talks by students and postdoctoral research associates at the University of Washington and CSE. Simon is the inaugural speaker in this session. What he's going to talk about today is designing an operating system for the data center, and I'll let you take it from there.
Thank you, Tom. I'm excited to be talking today. Hey, everybody. So today's data centers run a range of really popular applications, from web and cloud applications like Google, Facebook, Amazon Web Services, and so forth, all the way to big data and e-science applications that might be running on top of a distributed compute platform such as Hadoop. And as diverse as these applications might be, they all have one thing in common, and that is that they all push the performance and scalability limits of current data center server technology. They all have more users, more requests to satisfy, more computation, and more I/O to carry out. And while hardware designers have been making great strides to provide that kind of performance to data center applications, one of the main points of my talk today is to show you that the operating system is now the limiting factor to data center application performance. In particular, operating systems need to address a number of recent hardware trends, and I have the three most important ones up here that I would like to talk about today. The first one is that we have seen a tremendous increase in hardware I/O performance, both on the network as well as on the storage side. The second one is that hardware designers have been moving on to providing multi-core hardware architecture, so they're putting more processor cores on dies in order to scale performance rather than simply making processors faster. The final one is that we're also seeing an increasing integration of the I/O and memory subsystems of current server systems in order to gain even better I/O performance. And so what I'd like to do now is to go through these three hardware trends here in sequence, and for each one, tell you how current operating system architecture is already inadequate to deal with these trends, and then how to address them by building better operating systems. Starting with the first one, the trend of increasing I/O performance and the Arachis high I/O performance operating system that I've been building here at the UW together with a number of students as well as other faculty, and that has been published at a number of recent operating systems venues. So by now it should be clear that server I/O performance matters. Things like key value stores, web and file servers, lock managers, all these little applications that provide the basis for large-scale web services are principally measured by the latency and throughput with which they can carry out client requests. And knowing that hardware I/O performance has increased, I went ahead and asked the question, can operating systems actually deliver this hardware performance through to these applications? To examine that question, let's first have a look at a data center system. So here I have an example system, the Dell PowerEdge R520, which I'm going to use as a running example throughout the rest of this talk. And this is also the system that all of the evaluation that I will present has been carried out on. So let's have a deeper look at the system, starting with the I/O devices. First, we have a network controller. This is the Intel X520 dual-port 10 gigabit Ethernet controller. This is a fairly common network controller in data center servers today. Then we have a storage controller, the Intel RS3 RAID controller. And this RAID controller contains 1 gigabyte of cache memory that is backed by flash. So you can view this as a piece of persistent memory that we can write to really, really quickly through this controller. And finally, we have the Intel Sandy Bridge multi-core CPU that has 6 cores at 2.2 gigahertz. And the last time I checked, you could buy the system straight from Dell for around $1,200. So this is really a commodity data center server system, not some fancy, expensive new technology that I'm talking about here. Okay, so just to understand a little bit better what the I/O performance is that these devices are able to provide, let's conduct a little thought experiment. Let's assume that we're receiving 1 kilobyte sized packets at line rate at one of the ports of our 10 gigabit Ethernet device. In that case, we're talking about a packet inter-arrival rate at the server of 2 microseconds per 1 kilobyte packet. So that gives you an idea of what the headroom is that we have inside the operating system to do I/O processing. 2 microseconds is not a very long time. The story is similar for our RAID controller. The RAID controller is able to persist a 1 kilobyte size write operation to its internal cache memory within 25 microseconds. So while that is a little longer than the performance that the Ethernet device is able to give us, it's still not a very long time. So the takeaway is that today's I/O devices are really, really fast, much faster than they used to be. Still, though, we might be asking the question, can we just run Linux on one of these systems? After all, that should be the canonical choice for it. Well, let's examine that question. Let's look at Linux I/O performance. Let's take a popular data center server application. In this case, I took the Redis persistent key value store, which is commonly used to accelerate web requests and database lookups in data centers by caching these values in the store. You see that here at the top of the slide. Redis is able to serve client GET requests straight out of server memory for performance. And in addition to that, it can persist client SET requests via an operational log that is inside the application to disk via the file system of the Linux kernel. Below Redis then on the slide, you see the rest of the Linux I/O architecture. First, we have the kernel right below Redis, which, as is common for a monolithic operating system, sits directly on the data path between Redis and our two I/O devices here at the bottom of the slide. And just for reference, I left the two numbers from our thought experiment from earlier on here as well, because what I'd like to do now is to go ahead and benchmark Redis on top of this system configuration, sending it 1 kilobyte sized GET and SET requests. And then I'm going to measure what the time is that the server takes to process these requests. And I'm going to pop these results of this experiment up here in the Redis box now. First off, on the right-hand side, you see the total server-sided latency, processing latency for an average request, so 9 microseconds for an average GET request and 163 microseconds for an average SET request. So this is from the time the client request packet arrives at the server to the time the server sends the response back out on the network interface. Also, I have a breakdown of these numbers up here into the time taken inside the hardware to do the processing, inside the Linux kernel to do I/O processing, and inside the Redis application itself. And there are two takeaways from these numbers. First, looking at the totals, we can see that we're quite far away from delivering the raw performance of our hardware devices that we have at the bottom at the slide. To understand why that is, and this is the second takeaway, we have to look at the breakdown, and we can see that the Linux kernel is spending an awfully long time doing I/O processing, 62% for GET requests and 84% for SET requests. While of course, ideally, we would like most of that time to be either in the hardware or inside the Redis application. Now, to understand why that is, we have to remind ourselves that as a monolithic kernel, we have to invoke the Linux kernel each and every time we'd like to carry out an I/O operation on our I/O devices here, as it sits directly on the data path between us and those devices. And each time we invoke it, the Linux kernel has to go through a long laundry list of operations that it carries out on our behalf each time we invoke it, from multiplexing these devices to potentially multiple processes inside the system, to enforcing resource limits, to carrying out I/O scheduling, doing the actual I/O processing, carrying out access control, and so forth, each time we invoke it directly on the data path. So the takeaway from this is that kernel mediation is too heavyweight to deliver the raw performance of our fast I/O devices through to applications. So in the Arachis operating system, the goal instead must be to somehow skip the operating system kernel in the common case and deliver I/O directly through to applications, network packets, disk blocks, and so forth, to reduce the operating system overhead that I've just shown you on the previous slide. At the same time, however, we would like to keep all of the classical operating system features that such a kernel provides intact, because our users have grown accustomed to them and they become really important to them, such as the protection among various different processes, the enforcement of resource limits, the flexibility to roll out our own I/O protocols within the data center, or just a global naming system, such as a global file system. So how can we have it all? How can we skip the OS kernel to get better performance, but at the same time still keep all of the features that it provides? Well, it turns out that yes?
Why the protocol flexibility? Why couldn't the applications just, link in whatever dynamic libraries they need for that one? Why does this have to be part of your solution?
So the question is, why do we keep protocol flexibility in there? In fact, as I will show you, what we're going to do is link some of that functionality into applications where we can do it more efficiently. So that's going to come up actually. Okay, so it turns out that current data center server hardware can help us with this task quite a bit. And the keyword here is hardware I/O virtualization, which is already a standard on data center network interfaces, and it's an emerging technology on data center storage controllers such as our RAID controller. It turns out that there's a number of features already provided in hardware that we can adapt in an almost straightforward manner to provide some of the features that an operating system kernel had traditionally provided. For example, multiplexing. It turns out that we can already multiplex our devices to various different processes running within our system. Data center devices today support a standard that allows us to create virtual copies of devices on the PCI peripheral bus that each have their own registers, their own interrupts, so basically everything that we need to drive these devices as full-blown devices, except of course that they are provided by one physical instance of a controller. So for example, we can create virtual network cards, or VNICs, I will call them. And I will do this here now on the slide in an example. Let's just create 2 of these VNIC instances. So they're now full devices on the PCI bus provided by the physical instance. And in addition to that, we can also provide protection using some of the features that hardware provided. It turns out that we can now attach these VNICs to individual applications' virtual memory, so to restrict them to only be able to access the application's virtual memory region that we attach them to. And I'd like to do that now in this example here. So let's attach VNIC number 1 to the memory region of Redis, and VNIC number 2 to the virtual memory region of, say, a web server that might also be running inside the system. And this works through the system's memory management unit that is in there as well. Of course, in order to provide full protection, we also have to give the flip side, which is to restrict applications from carrying out arbitrary I/O on these virtual devices. We only want them to be able to carry out I/O operations that we deem them eligible to carry out. So just to give you an example again, the web server, for example, should only receive packets that are destined to it. So we would like only TCP port 80 packets to go to the web server. And again, it turns out that our I/O devices can provide that. The X520 NIC contains packet filters that program what you can think of is a little switch that sits on the network device that will then steer traffic according to the filter that we have provided to one of these VNIC instances. So in order to, for example, steer web server traffic to the web server, we would install a filter for TCP port 80 into the switch and direct the traffic to VNIC number 2, which is the one attached to the web server. And the switch will then make sure that that traffic only goes to the web server. Similarly, we can install filters to drop everything that doesn't fit that signature that is crafted by the web server, so that we can restrict the web server from crafting arbitrary I/O packets. The story is similar for the RAID controller. RAID controllers traditionally provide something that is called a logical disk, and logical disks are just virtual mappings to a subset of the physical disk space that is attached to the RAID controller. And again, we can just program these directly in order to point to exactly the bytes that we want an application to access, to be eligible to access. The final thing is I/O scheduling, which also can be provided in hardware. Our NIC, again, contains rate limiters as well as packet schedulers that we can directly program according to a system administrator's I/O scheduling policy, and thus restrict those virtual NIC instances, and with that the application from crafting packets too fast, for example, restricting them to a particular rate. So with that in mind, it actually becomes fairly straightforward to skip the operating system kernel in the common case. The first thing that we're going to do is move these 3 things here, protection, multiplexing, and I/O scheduling, down into I/O devices where we can already attain them. We then move the API and the I/O processing up into applications, whereas we will see later we can do them much more efficiently. And the way we do this is by just putting them into a library, as the question already came here, into a library, and then link that library into applications. So we don't really need to modify the applications at all. Finally, because I/O devices are now also able via the MMU to access application virtual memory directly, all of the copying that the Linux kernel traditionally has to do in order to multiplex devices and protect them to different applications completely falls out of the picture. We can build a very fast, what we call a zero-copy I/O stack with this architecture. And that leaves us now with these 3 things here still in the kernel: naming, in particular global naming, the configuration of resource limits, and access control. So let's see if we can also somehow move that aside. We're going to get back to that a little later, but first let me clear up the slide here a little bit. So this is now the same slide, just reorganized for better readability. And this gives us the Arachis I/O architecture, where you can now see that the kernel is completely off the data path between applications and their private I/O devices here in this architecture. And in Arachis, we call this split of the operating system the control plane, which is where the kernel operates, and the data plane, which is where the applications and our I/O devices operate. And the idea is that the control plane will only be invoked very infrequently in order to set up the direct data path connections between applications and their I/O devices on the data plane. And that connection on the data plane can then be very, very fast. So what I'd like to do now is to go into a little bit more detail about what these components now have to do that we have this new architecture. I already covered the I/O devices, so next I'd like to talk a little bit more about what the kernel now has to do. And as I said, we now still have these three things inside the kernel: naming, access control, and resource limits. The easy two are access control and resource limits, so I'd like to talk about them first. Access control we now only have to do once when we're configuring the data plane. At that point, we're figuring out what the total set of operations is that an application should be eligible to carry out. And we then enforce that by programming the NIC filters and the logical disks. And from that point forward, the hardware can enforce that access for us. Resource limits work similarly. We just program the hardware I/O schedulers according to the system administrator's I/O scheduling policy. Global naming then is the harder one. We'd still like to provide users with a global file system. So we retain the virtual file system implementation still within the kernel. So this is where all the naming happens inside Arachis. But of course, because all of the I/O processing is now in applications, the implementation of the actual storage behind those names is now happening within applications. So how do we resolve that dichotomy? To explain that, I'd like to get back to the Redis example, which you see here on this slide. On the top left-hand side, you have Redis, which in this example already has its own private virtual copy of the RAID controller mapped into its virtual address space, and it can use fast hardware operations directly on that copy to carry out its I/O, potentially via a library. The area that the Redis application then is carrying its I/O out on, we call a virtual storage area. And the idea here is that this is just a linear mapping of a potentially fragmented physical disk space that is directly provided by one of the logical disks that is implemented by the RAID controller. And so on that virtual storage area, Redis can now carry out its I/O operations and store objects. And in addition to that, it can assign names to these objects. And it can register these names with the kernel virtual file system, which you see on the lower left-hand side. So in this example, it might have a log file, the actual key value database, and a configuration file in its storage area. And all of these names it has registered with the kernel virtual file system. So then let's assume that we'd like to edit the configuration file in Redis. So we fire up our editor, Emacs. And Emacs, of course, now has no idea in what format that data is stored, because it was the Redis application that stored that data in the virtual storage area. So what Emacs is now going to do is first, fairly straightforward, it will just do an open system call to the configuration file, to the kernel. And the virtual file system now knows that Redis was the application to create that data in the first place. So it is going to redirect the Emacs application via a POSIX-compliant inter-process communication interface to access the file via the Redis application. So this is how we resolve the global naming and storage issue. Now I'd just like to give you a highlight on one of the cool things that we can now do on the data plane now that we have the API and the I/O processing directly within applications. There was a question?
Yeah, just a quick clarification.
Yeah.
Did we need to modify Redis at all in order to allow that indirection to happen?
So the question is, would we need to modify Redis at all for the indirection to work? So the idea here is that applications would typically just link a library that provides all of the fast I/O processing, though that application programmers don't really need to implement all of that, and that it's the library that will provide that interface for other applications to then do the indirect access. Yeah. Okay, so one of the cool things that we can now do within applications, now that we have the I/O processing and the APIs local to individual applications, is to modify the API a little bit and tailor it more to these applications for added performance. And my highlight here is on the storage data plane, where we can modify the API for better performance for the Redis application. And what we have been doing here is to provide something that we call persistent data structures for Redis. What are persistent data structures? Well, you can think of them just like regular data structures. Examples might be a log or a queue, except that most of the operations that Redis is going to execute on these data structures will be immediately made persistent on the backing store on disk. And this approach has a number of benefits. First of all, it allows us to make the in-memory layout of these data structures equal to their on-disk layout, which eliminates all of the marshalling that applications traditionally have to do when they serialize a data structure from an in-memory representation to an on-disk representation. It also allows us to keep all of the metadata that we require for persistence of the data structure straight within the data structure entries themselves, which allows for their early allocation, for example. Just to give you an example here with Redis and the log, when Redis calls the allocate a new log entry in memory operation, we can already allocate all of the metadata for its eventual persistence with that call in anticipation that Redis will soon call the append to log operation, which is the actually persistent operation. And then when that operation is called, we can flush all of the metadata out together with the application data in one write operation, which is due to better spatial locality that we can also achieve with these data structures. If you compare that with what a file system has to do when it does persistence, it has to do at least 2 write operations because it will typically persist an inode table, which is stored completely separately from the application data in addition to the application data. On the read side, we can then also do some data structure specific caching and prefetching. And this is due to the higher level semantics of the data structure. To get back to the log example, because the log API only allows us to read the log sequentially, we can do serial prefetching of log entries here. And so now to show you that this can have performance benefits, we went ahead and modified the Redis application to use our persistent log implementation instead of its own log implementation. That was a fairly straightforward change. It consisted of 109 lines of code changed inside Redis, mostly just to rip out Redis's log implementation and put our log in. The APIs were exactly identical because they're both logs. And this now resulted in great performance benefits that I will show you now. Firstly, focusing on latency inside the Redis application, we were able to reduce the latency of in-memory get operations. So this does not yet include the log. This only includes a library network stack that bypasses the operating system kernel by 65%, from 9 microseconds in Linux down to just 4 microseconds inside Arachis. And then we were able to reduce the latency of persistent set operations, so this also includes the log, by 81%, from 163 microseconds on Linux running on top of the extended forth file system down to just 31 microseconds in Arachis. And as you can see here in the breakdowns now, we're also spending a lot less time inside the Arachis library I/O stacks to do I/O processing. We reduced the time from 62% on Linux for a get operation to 35% on Arachis, and from 84% in Linux for a set operation to just 7% in Arachis. And these latency improvements then result in great throughput improvements as well. We were able to improve the throughput of get operations by 1.75x over Linux, and that of set operations by a grand total of 9x over Linux. And just to show you that the hardware is now the bottleneck again, we went ahead and emulated an even faster storage device that only had 15 microseconds access latency, which is equivalent to that of the fastest storage device on the market, by using a write delaying RAM disk. And we were measuring that the set operation throughput on Redis was improving proportionally to the reduction in latency. Our library I/O stacks also have great scalability with an increasing number of cores, which I'd like to show you here using the memcached in-memory key value store. The reason for using a different application here is simply that memcached is a multi-threaded application, so it can actually make use of multiple cores, while Redis was only a single-threaded application. The benchmark that we're running on top of memcached is basically identical. We're sending it set and get requests in some mixture, and then measure the throughput with which the memcached server can respond to these requests, which I'm showing you here in thousands of transactions per second on the y-axis. And on the x-axis, we have a scalability graph. As we increase the number of CPU cores available to Redis, we can see how the throughput is impacted by that. And we're comparing memcached, executing on top of the Linux application, which is the Linux operating system, which is the blue bar, to that executing on top of Arachis, which is the orange bar. And you can see here that even on just a single CPU core, we achieve a speed up of 1.8x, which is again due to the fact that we're using a library I/O network stack that is bypassing the kernel and can be simpler because we can tailor it to the memcache application. As we then increase the number of CPU cores, we can see that memcache can scale linearly on top of Arachis up until it hits the line rate of our 10 gigabit Ethernet interface, which is the top y-axis line, and at 4 cores, and achieves a speed up of 3.1x over the equivalent Linux configuration. Linux does not scale all too well. It basically tapers out after around 2 cores and then stays flat. And the reason for that is that Linux's network stack, as it's globally shared by all applications, has to provide all sorts of features to all conceivable applications out there. So they end up with a much more complex structure of their network stack that has much more complex data structures, and so more locks around these data structures and also more complex algorithms, all of which we can eliminate because we can include only the features that we need for memcached to function. And so that's how we can eliminate a lot of locks inside our data structures as well and scale better. There are also a number of current potential limits in the hardware to production use of the Arachis approach that I'd just quickly like to highlight now. For example, the expressivity of filter instructions or the filters in our commodity network interface card, such as our X520, is still fairly limited today. Right now, the X520 is only able to filter at the Ethernet MAC layer, while obviously we would like it to be able to filter at higher layers as well, such as the IP and the TCP layers. However, that functionality is already provided by more expensive NIC implementations, such as the SolarFlare line of cards. So I imagine it'd only be a matter of time until the more commodity NICs will support these as well. Similarly, our RAID controller was so far not yet able to provide hardware protection among the different logical disks that we configure, so we had to provide that feature by dedicating a server core to do so, which had an overhead of 2 microseconds, which was not included in the numbers that I presented earlier. And again, I envision that this will be provided soon by RAID controllers and other storage devices, because it is also very helpful in speeding up virtualization scenarios, which is what some of this technology has been developed for in the first place. So to summarize Arachis, I've shown you that the operating system is an I/O bottleneck to data center server applications. And the reason for this is that these globally shared I/O stacks, such as in the Linux operating systems, are slow when they're directly involved in the data path between applications and I/O devices. So in Arachis, we split the operating system into a control plane and a data plane component that allows us to do direct application level I/O on the data path and build these specialized I/O libraries to get even better performance out of applications. And I've shown you that these application level I/O stacks can deliver great performance. I've shown you, among other things, that we can achieve up to 9x throughput improvements over Linux for the popular Redis key value store and an 81% speed up in terms of latency for that store. They can also scale very well. I've shown you that memcached can scale linearly on top of Arachis up until it hits the line rate of our Ethernet interface and achieves 3x the throughput of the equivalent Linux configuration. The source code to Arachis is available. You can go to arachis.cs.washington.edu if you're interested to have a look, or even better yet, if you want to include it in your own research. So now I'd like to switch over to the second hardware trend, multi-core hardware architectures. Oh, there was a question there, yeah.
So it seems like you very effectively reused hardware features, like these virtualization and resource limits that were originally designed for other purposes.
Yes.
What were those other purposes?
So some of those purposes were to bypass hypervisors and virtualization scenarios. And so you could view it as we're taking a further step and not just bypassing the hypervisor, but also bypassing the operating system kernel to get the performance all the way into applications, yeah. Okay, so second hardware trend, multi-core architectures. And the problem, operating system performance on multi-core hardware. This was part of my PhD and has been published in a number of venues around that time. So I think we can all agree that multi-core hardware is here. Hardware designers are putting more processors instead of faster processors on dies. Now, unfortunately, this trend towards multi-core brings with it a rather fast pace of software-visible hardware architectural changes. Basically, every 1.5 years, whenever Intel or AMD release a new multi-core hardware architecture, we have to adapt and change our software to still be able to scale performance with that new hardware architecture. And now operating systems developers struggle very much to keep up with these developments. There's an extreme engineering effort being put into current operating systems like Linux and Windows to have them work on current multi-core hardware architectures, and it's projected that that effort will even have to increase in the future. This is a structural problem. Linux and Windows are complex monolithic programs that have been designed in the early 90s with uniprocessors and simple multiprocessors in mind, and these grave changes to the hardware architecture that is visible to software were just not around at the time. So I and a team of researchers at Microsoft Research and ETH Zurich decided to start from scratch and build a new operating system that we call Barrelfish to address this set of issues. And before I continue, I'd just quickly like to point out that while it might seem like it requires a huge upfront investment of engineering costs to build a new operating system, my experience is that that effort was paid back many times because, for example, it allows for Barrelfish to be a clean slate basis for further operating systems research on modern hardware architectures. And in fact, the Arachis operating system that I just presented is based on the Barrelfish code base, which tremendously reduced the amount of time required to build out Arachis from an idea to a publishable product. So to get back to the problem, software visible changes inside the hardware architecture. These changes can be broadly classified into two main categories. The first one is the complexity exposed by just a single multi-core system configuration. That mostly boils down to non-uniform memory access latencies, NUMA domains, and cache hierarchies. NUMA is an abbreviation for non-uniform memory access, and that simply means that we now have memory banks that can be closed to certain processors, and it's simply cheaper in terms of performance to access the memory that is closer to that particular processor making the access than it is to access memory that's further away. The story is fairly similar for cache hierarchies. Today's multi-core processors contain quite complex hierarchies of different cache memories, sometimes up to 4 levels deep. And again, it's simply cheaper to access a particular piece of cache memory if it's closer to the core making the access. Just to make this more concrete, I have this table here that shows you for all the different memory types inside the Intel Sandy Bridge dual socket architecture, what the access latency is from one particular core inside that system. And I'm showing it to you both in terms of nanoseconds, so in absolute terms, as well as normalized to the access latency of the cache that is closest to that core, which we also call the L1 or the layer 1 cache. And the takeaway from these numbers is that access latency can vary up to 100x depending on where the data is inside our system that we're trying to fetch and from where we're fetching that data. Also, I'd like to point out that the hardware memory interface is a synchronous one. So the CPU making the access is stalled throughout the entire time that we're fetching the memory from that remote location to the processor making the access. So I think that makes an excellent case for pointing out that it's really important to place operating system data structures on memory that is close by to the core that is making the access. And this is something that traditional shared memory operating system architecture is oblivious to. The second set of changes in the hardware architecture comes down to the sheer diversity that we now have of these different multi-core systems that are all different to software, starting with just the memory interconnect. The Sandy Bridge architecture that I've just shown you uses the Intel QuickPath interconnect, which has a ring-like structure. So this determines where the caches are in the system and how long it's going to take us to access a particular cache. If we're accessing a cache that's on the opposite side of the ring, then we have to go all the hops around the ring to fetch it, and that will increase the latency proportionally. AMD-based systems are entirely different. They're based on the hypertransport interconnect, which has a mesh-like structure. So you can kind of see how we have these different network-like effects now of our memory hierarchy, depending on what the topology is of these different caches and CPUs, and where the data is that we're trying to access. We're paying an overhead according to that network. Also, we have an increasing diversity of different cores that we have to deal with. For a long time now, we've been integrating GPUs together with CPUs on processor dies, but in the near future, it's very likely that we might also integrate FPGAs as well as other more programmable accelerators within a single multi-core system. Also, on a single die, we already have what are called asymmetric architectures, such as ARM's Big Little architecture, where there is a large number of rather wimpy cores integrated together with a small number of fairly beefy cores that have different power envelopes and are optimized to executing certain parts of a program more efficiently. And the natural question that arises here for an operating system developer is how do we even run on all of these different heterogeneous cores and provide a single system image to our application developers, which is the abstraction that they're traditionally programming against. Traditional operating systems cannot support that. They will only run on the CPUs and then treat everything else as a high latency device, which is simply not true anymore. These devices are now highly integrated with the system and are fairly low latency. So in the Barrelfish operating system, we decided to start over and propose to structure the operating system as a distributed system instead that can run on this kind of network of different cores and caches. And we termed this architecture the multi-kernel. And we achieve it by following a simple set of 3 design principles. First of all, we make all inter-core communication inside the operating system explicit. We then make the operating system structure hardware neutral as opposed to designing it for one single multi-core system configuration. And we then view all operating system state as replicated instead of shared. So very similar to how you would design a distributed system. We achieve that by carrying out all of the communication inside our operating system with messages. There is no more shared state inside the Barrelfish operating system. This has the effect that it decouples the operating system structure from that of the memory interconnect. All of the communication patterns inside the operating system are now explicitly expressed, which means we can reason about communication happening within our system, and we can measure how long it's going to take to communicate between different cores or to fetch a piece of memory from a cache that is further away. It also naturally supports heterogeneous cores. We can simply compile a new operating system node that is compiled for that particular instruction set architecture of the code, and it can still use message passing to communicate with the other nodes inside the system. And we can also support non-cache coherent interconnects simply because we're doing message passing, which does not necessarily require cache coherency. Of course, it is required for shared memory data structures. If you have caches, you need coherence among those caches for them to work. Finally, it also allows for split phase operations, which means we can now decouple requests and responses from each other to gain more concurrency inside the operating system. So there are no more core stalls on shared memory locations. In Barrelfish, we can simply send a message to another operating system node, carry on with our business, and as we receive the response back, at that point we can attend to the response, as opposed to having to wait for each shared memory location that we're accessing. I think there was a question over there.
So I'm just trying to understand, are there partial failures on multi-core chips?
They're not, and I guess I should repeat the question first. Are there partial failures on these chips? That's, of course, a thing that a problem that distributed systems are worried about. So this is one of the crucial changes between the design of distributed systems and the design of this distributed operating system for a single machine. We can actually simplify some of the algorithms that we run inside and the message passing that we run inside the operating system and optimize it more, because we can assume, at least that's what we're doing, that the host will be a single failure unit. So it will either fail altogether or it won't fail at all, which is true for current multi-core machines. That said, though, if in the future, at some point, multi-core machines will become so complex that we might have individual failure domains, then the Barrelfish design is a nice design to kind of start from if we want to design an operating system that can still keep running just in the same way a distributed system would be able to continue running on a cluster of machines. Yeah. Okay, so using message passing then allows us to separate the operating system structure from that of the hardware. In fact, the only hardware-specific parts inside the Barrelfish operating system are the implementation of the different message transport mechanisms, as we can optimize those to the underlying interconnect, and something that we call CPU drivers, which is simply the part of the kernel that deals with the peculiarities of one potentially heterogeneous core, such as the way that core deals with interrupts or the certain instruction set architecture of that core, as well as device drivers. But that's the same thing in monolithic kernels as well. And this then allows us to adapt the operating system to the changing performance characteristics of current and future multi-core systems. We can simply place operating system components on cores that are close to each other for our definition of close, which is low latency communication between these different components. And we can simply determine this at boot time of the operating system. At that point, we can measure what the topology of a particular multi-core architecture is, and then place these components on that architecture without having to invest any further engineering effort in order to change our software to somehow adapt it to that new structure every time a new architecture comes out. So with that, we arrive at this architecture, the Barrelfish architecture, which you see here on the slide. Starting from the bottom, we have the memory interconnect of our system, which can be quick path, can be hypertransport, can be something else. Top of that, we have our cores, which are potentially heterogeneous. On top of that, then, we have the multi-kernel, which, as you can see here on the slide, is now sliced up into these individual operating system nodes. There's one per core that we're running on. And these nodes might contain a sliver of architecture-specific code, as well as a replica of the state that is relevant to that node, to the execution of that node. And we keep that state consistent using a number of agreement algorithms, just like in a distributed system, that can communicate via asynchronous messages on top of the memory interconnect. On top of that, then, the world is unchanged. We can still run legacy applications that might use shared memory and can use the regular operating system call interface and just benefit from this more modern operating system structure. And the structure has some performance benefits. I just have a few highlights here in the interest of time. First of all, low-level operating system operations can scale better on the Barrelfish operating system than, say, on Windows or Linux. We were able to demonstrate that the latency of a memory unmap operation, for example, which is a fairly common low-level OS operation, can be up to 2.5 times faster on a 32-core machine than that on Windows, for example. You can see the numbers here on the slide. We also demonstrated that there is no penalty for running these legacy shared memory applications, which we verified by running the Splash and the NASA OpenMP benchmarks, which are compute shared memory benchmarks that showed the exact same performance and scalability on Linux and on Barrelfish. However, we can speed up certain data center server applications, such as a web server. We were able to demonstrate a 2x speed up of a web server over the same configuration running on Linux, which was due to the fact that we can attain more concurrency via these split phase operations due to message passing. In Barrelfish, we were simply running the Ethernet device driver on a separate core that was close to the core that ran the web server and had the two communicate via message passing. That allowed us to use the extra concurrency, which is something that would be really hard to achieve in a shared memory operating system. So to summarize Barrelfish, I've shown you that modern computers expose network effects, and that current operating systems do not match this structure. So I and a number of researchers at Microsoft Research and ETH Zurich designed the multi-kernel, which is a model of the operating system as a distributed system that uses explicit communication and replicated state to achieve a more hardware-neutral operating system structure. And we demonstrated by building it, which is the Barrelfish operating system, better performance as well as backwards compatibility to legacy applications. I've shown you better scalability of common operating system operations as well as some applications, and the equivalent performance for traditional shared memory applications. There's a question up there.
So are there examples of applications that were originally written for a centralized operating system like Linux, and that make some assumptions about the synchronization going on within the kernel? And if you were to plot that application on top of Barrelfish, where there's all of a sudden less, not necessarily as much coordination between cores, between the kernels, I'm trying to understand, are there examples of applications that were written for Linux that would not work on Barrelfish because they're making some assumptions, some implicit assumptions about coordination?
Okay, so the question is, are there examples of applications that would have been designed with the assumption of running on top of Linux and then wouldn't execute on top of Barrelfish? I don't know of any, mostly because the interface that we can provide to them is the POSIX interface, would be the exact same interface. And of course, you can always try and guess something about what the operating system does, but applications also want to be portable, so they only do this to some extent. And the POSIX interface will give you what the interface specifies, and if you deviate from that, then either you will only run on one particular operating system, but most applications won't do that precisely because they want to provide, they want to be able to run on other configurations of operating systems that provide POSIX too, and that's why most of them, all of them that I know of, will run on Barrelfish as well. Yeah, I think there was one question there.
How does this differ from something like MOSIX, which was more of the distributed system?
I'm assuming that MOSIX is one of the distributed operating systems around the 90s, like Amoeba and these.
You say I have 32 computers, so I have 32 threads.
Right. So exactly. So there has been a line of research in the 90s where people were actually building distributed operating systems that ran on a distributed set of computers and exposed that almost as if it was a single machine. The difference between Barrelfish and these operating systems is that the trade-offs of the hardware architecture that they ran on are different ones. So for operating systems like Mosix, you have to take into account that individual servers might actually fail, and so that influences the way in which you design your message passing and your agreement algorithms inside the operating system. And so you kind of have a different trade-off of what performance you can achieve versus what assumptions you have to make over what machines can fail, for example, in the system.
But is there anything that limits Barrelfish from extending to actually?
No, and I mean, you would have to start thinking about things like failures. It's kind of getting into the previous question, I guess. But Barrelfish would be a nice base to definitely like build out into more computers inside the data center. Yeah, definitely. Okay. Source code of Barrelfish also available. You can go to barrelfish.org if you're interested. So that brings me now to the final hardware trend, the integration of I/O and memory systems, and this is now going into future directions. So as I said, there are many more hardware changes that impact the operating system, and I/O memory system integration is just one of them that I'd like to spend the rest of my talk time on, but there are many more. For example, for the first time, we now have fast storage devices that are based on non-volatile memory technologies, and that's putting great pressure on the performance and scalability of operating system storage stacks that I think is interesting to investigate further. Also, kind of looking out further into the greater data center from one machine. We now have much better switching technology that allows to reduce what is called network-induced tail latency. Tail latency is simply the subset or is describing a problem where a subset of operations in a web service, for example, that is small but still significant, take significantly longer to execute than the average of that service. And this is something that big web services like Google and Facebook are grappling with because it's turning their users away from them. And while networks induce some tail latency that we can now mitigate with these switches, the operating system also induces tail latency. And so I think that's kind of the next spotlight where we could look to see if we can reduce that and introduce tail latency. Also, because we're now increasingly bypassing operating system kernels to gain more performance inside applications, operating system functionality is increasingly moving into these applications. And so that requires application developers to understand operating systems concepts a little better. Maybe not to the point where they have to implement them, but at least to the point where they have to choose between different libraries that might be offered to them that each have different performance trade-offs that they need to be able to evaluate. And so I'd like to quote Tom Anderson here, who said this aptly at his keynote at the Symposium on Cloud Computing in 2014. We're all OS developers now. So I think this makes an excellent case for pointing out that it's a really exciting time to be an operating systems researcher. We now have many changes inside the hardware architecture, but also inside the software architecture that impact the way we design and deploy software systems, not just in the operating system, but all the way up to applications. And so now I'd just quickly like to give you one highlight on one of the things that I'd like to do in the future, and this is on I/O and memory system integration. The reason we're doing this is that it allows for much tighter integration of the I/O subsystem with the memory hierarchy and the cache hierarchy of a server machine. So we could, for example, send network traffic directly to an L1 cache of a particular core where that core can access that data much, much quicker. And the reason we're doing that is that we kind of have to, because network speeds still keep on increasing. We're going from 10 to 40 to 100 gigabits. And as we do that, accessing data from a particular server core to a cache that is too distant or is further away from it might be too slow. It might prevent that software from catching up with the tremendous speed that we can now inject network traffic into our machine. However, in order to get this tighter integration, I claim that applications need much more fine-grained control over how data is routed to cores and where to put that data, or even just a portion of that data than they have today. Hardware then must handle the fast execution of these I/O operations. We clearly can't have a piece of software in the middle anymore that does the steering based on application information, as that would be too slow, as we've seen in the Arachis part of my talk. So my proposal here is to rethink, for example, the network I/O interface and make it more flexible. In particular, I'd like to be able to have applications to insert packet matching rules into the network interface card that can inform its I/O actions based on, say, application-defined packet fields, so fields inside the network packets. This is not a very far-fetched idea. In fact, this is something that OpenFlow switches have been doing for a while. They're introduced in data centers to provide things like software-defined networking, and they use this packet matching to decide what output port to send a particular packet to based on application-level packet fields, application-defined packet fields. So I'd like to apply that idea to the design of the network I/O interface, and so have I/O actions that can steer network traffic to host memory based on these application-defined fields to select what subset of a packet we want to get to a particular memory region and to what cache we might want to send that packet to. And that has a number of use cases. I just have one highlight here. It allows us, for example, to build much more cache-efficient software. So this example here is on a more cache-efficient key-value store, where you can imagine that we can now partition the data in the store over a number of caches inside our system, and then use a packet matching rule to steer the incoming get and set requests from clients directly to the core that we know has the value that is being accessed by that get or set request hot in its cache. That's something that a traditional network interface is not able to do. It would just randomly assign the connections to the different cores, and so that would have the overhead that we would then have to pull over the cache lines that we know is hot in a cache somewhere else to that cache that has the connection that is trying to access that. So this is just one of the many examples of use cases that we can have with this interface. But I'd like to summarize the talk now. I've made the case that data centers have very high demands for performance along all the different axes of performance, processing, more network I/O, more storage I/O. And while hardware designers have been making great strides to provide that kind of performance to data center applications, it's now the operating systems that need to catch up with these hardware developments. And I've shown you two ways to catch up with these developments, the Arachis high I/O performance operating system and the Barrelfish scalable multi-core operating system. And I provided an outlook on another hardware trend that I'd like to investigate in the future using more flexible network I/O. In general, my approach is to build research operating systems and make them available to the public domain, with which I had great success so far. The Barrelfish operating system, for example, had more than 20,000 code downloads in the years 2009 to 2012 alone. And my operating systems have also garnered significant media and researcher interest, as well as fostered strong collaborations with industry that are still ongoing, among them with Intel, HP, and Huawei. There's even more operating system and networking research available on my webpage. If you're interested, you can go to faculty.washington.edu/SimPeter. And with that, I'd like to say thank you, and I'm happy to answer any more questions you might have.
Okay, questions? Yeah.
So when you're talking about Arachis, I understood that a lot of the overhead in Linux comes from all this functionality that's in the Linux kernel, but I've seen various people do work that has stripped out functionality from the Linux kernel and gotten massive speed improvements from doing that. Do you have an intuition about how Arachis might compare to such a stripped down Linux kernel?
Yes. So that brings me basically straight to related work, which I have here. There have been approaches in the past to bypass operating system kernels, particularly on the network side, because the network kind of perpetually has been a little bit faster than the CPU over the years, and then kind of rebounded and then came back, and now we're again at this stage. However, the difference between Arachis and those approaches is that we now have a lot more functionality available in hardware. That's mostly due to the fact that Moore's law is still continuing, and we just have much more transistor space available, so we get all of these features almost for free inside hardware. And so previous approaches have either tried to do this by still keeping the classical OS architecture intact, where you still have the kernel and you need to invoke the kernel, so you have this overhead of going into the kernel and out, and there are many ways you can try and mitigate that overhead. NetMap is, for example, one recent piece of work that has done this, where applications can access device registers directly via device file, kind of the classical way you make that available in a Unix operating system. But they still have the system call interface, and they mitigate that overhead, which is basically comes both direct and indirect. You can have the direct system call overhead, but then also the overhead of the cache access latency. You're kind of polluting your cache if you're going into the kernel and back by batching system calls, which is a trade-off that they have to play that favors throughput over latency. And we're specifically targeting these kind of low latency server applications as well. And so latency there really counts. And so that's why these other approaches don't work there as well as the Arachis approach.
Other questions? Oh, yeah, go ahead.
I'm curious if you've looked into the applications for Arachis in essentially data center distributed storage frameworks, essentially, that's not the word, appliances, in the sense that EMC and these other pre-built storage systems, SAN appliances, are very, as of recent, moving towards a more commodity Linux-based system as opposed to customized specific hardware and software. In that sense, has a partnership between Arachis and its development been thought of regarding EMC, or maybe in terms of more open source, Ceph, if you've heard of that, or Gluster?
So we haven't, at least in research, we haven't evaluated that yet, although this is an interesting area to look into. Very curious to see how we can improve the performance of those. And yeah, Arachis is open source, so we can definitely collaborate with them. We're in fact talking to various companies right now, not exactly in that space, but in similar spaces, to see if we can get the technology into production use.
Anna.
You talked about using OpenFlow like packet matching right at the end. Where do you see the cutoff between kind of the complexity of doing IP or application level packet processing in the hardware versus doing it at the application level or somewhere else?
Right. So obviously we can't put all of the processing into the NIC. I mean, we could try that, but that wouldn't defy the purpose. I guess what gives us great confidence is that these OpenFlow switches can already provide this at high line rates. So we know that it's technically possible to achieve just application level packet matching on arbitrary packet fields. And so that's the kind of the hardware architecture that we'd like to start out from. And we have actually identified a great number of different use cases that can benefit from just this packet matching on application level defined fields, more than what I've shown in the talk.
Okay, let's thank the speaker and